In this talk, I'm going to describe an algorithm for sampling a polytope that mixes in order n square steps. Given a polytope B in n dimensions described by ax greater than equal to b with m constraints, the goal is to generate a nearly uniform sample from P. Sampling convex bodies is a fundamental problem and a basic ingredient of algorithms for optimization, integration, linear programming, approximate counting, volume computation, etc. Two of the most widely used polynomial time sampling algorithms are the ball walk and hit and run, which work for any convex body. Ball walk is a Markov chain where given the current point x from a ball of radius r centered at x, we select a point y uniformly at random. If y belongs to the body, we move to y. The radius of the ball used is some constant divided by square root n. Before discussing the running time, a few notations. A convex body is called capital R by small r rounded if it contains a ball of radius r and is contained in a ball of radius big R. For an R by R rounded polytope, both ball walk and hit and run makes an order n square r square by small r square time from a warm start. Both of these algorithms are not affine invariant, and for the runtime to be truly polynomial in M and N, they need an expensive rounding step to bring the body to an isotropic position. Another drawback is that the step size cannot be too large, otherwise the rejection probability for points at the boundary becomes too high. To fix these problems, an alternative could be to use a different ellipsoid to sample at every point. This requires for these ellipsoids to be in the polytope and be affine invariant. That is, after an affine transformation of the polytope, the ellipsoid for a point x should be the same as the old ellipsoid for this point x after the same affine transformation. An example is to use John's ellipsoid, which is the maximal volume ellipsoid contained in a convex body. However, it is expensive to compute, and the mixing time of a walk based on John's ellipsoid is order n to the power 7. Turns out we can do better by using John-like ellipsoids, which are faster to compute. We are going to describe the Dickin walk, which uses barrier functions to define the ball and build on that. A barrier function is a convex function on the interior of a polytope that tends to infinity towards the boundary of the polytope. A barrier function f can be used to define Dickin ellipsoids. For a point x in the polytope, EXR is the ellipsoid centered at x with matrix Hessian of f at x and having radius r. These ellipsoids are contained in P and are affine invariant depending on the properties of the function f. Before defining the standard Dickin walk, we need a few more notations. For a point x in the polytope ax greater than equal to b, the slack matrix Sx is a diagonal matrix whose ith entry is the slack corresponding to the ith constraint. For a vector h, the local norm at x is equal to the square root of h transpose capital Hx h, where capital H is a positive semi-definite matrix, which will be clear from the context. Now to the definition of Dickin walk. The function fx equal to sum over all constraints of minus log ai transpose x minus bi is called the log barrier. The Hessian of the log barrier is given by the matrix A transpose Sx to the power minus 2a, which is a positive semi-definite matrix. Given a starting point x naught in the polytope, the Dickin walk can be described as follows. For the current point x, from the Dickin ellipsoid centered at x, pick a point y uniformly at random. If x belongs to the Dickin ellipsoid of y, we move to y with probability minimum of 1 and the ratio of volumes of Ex and Ey. A theorem of Kannan and Narayanan bounds the mixing time of standard Dickin walk as if K is an n-dimensional polytope defined by m linear constraints. The mixing time of the Dickin walk is order mn from a warm start. One of the results of this paper shows how to implement every step of the standard Dickin walk in O tilde n square plus number of non-zeros and A operations. However, due to time constraints, we will not go into detail of this result. The standard Dickin walk is affine invariant, and however, note that the mixing time depends on m, which can be exponential in n. For example, take a hypercube in n dimensions and duplicate one of its facets m minus n times. Consider a square in two dimensions described by 4 constraints. If we repeat the bottom constraint 3 extra times, it causes the axis length of the ellipsoids to shrink in the perpendicular direction, effectively reducing the step size and hence increasing the mixing time. An idea to fix this is to assign a weight to every constraint such that the sum of weights is order n rather than m. So instead of using a matrix like A transpose Sx to the power minus 2a to define the ellipsoid at point x, we would like to use a matrix of the form A transpose Sx inverse Ws Sx A. However, this would require additional properties on the matrix function to ensure fast mixing, which we will discuss in the next section. This leads to a natural question. Is it possible to sample a polytope in time that is independent or only logarithmically dependent on m? The answer is yes, and the next section describes an algorithm to achieve this goal. The generalized Dickin walk for a matrix function H is defined as follows. Let EXR be the ellipsoid centered at X with radius R and variance matrix HX. For the current point X, we pick a point Y uniformly at random from the Dickin ellipsoid of H centered at X. If X belongs to the Dickin ellipsoid of Y, move to Y with probability minimum of 1 and the ratio of volumes of EX and EY. Usually, H is the Hessian of a self-concordant barrier function, as in the case of the standard Dickin walk. However, to ensure polynomial mixing, H does not necessarily have to be the Hessian of a barrier function, as long as it satisfies certain properties. Our main result proves fast mixing for the generalized Dickin walk, satisfying certain properties, which we will define shortly. Theorem 1 states that the mixing rate of the Dickin walk for a nu-bar symmetric, strongly self-concordant matrix function with convex log determinant is order n nu-bar from a warm start. Theorem 2 states that there exists a weight function Wx such that the mixing rate of the general Dickin walk using Hx equal to A transpose Sx inverse Wx Sx inverse A for any polytope in Rn is O tilde n square from a warm start, and each step can be implemented in O tilde mn to the power omega minus 1 arithmetic operations. We use the Lee-Sitford barrier defined in Lee and Sitford 2019 to define this weight function. Compared to previous results, the weighted Dickin walk based on the Ellis matrix is currently asymptotically the fastest method for uniform sampling from a polytope. We present a high-level overview of the proofs of these theorems. To prove fast mixing, we bound the conductance of the Markov chain defined by this walk. The conductance of a Markov chain is defined as the minimum of the probability of escaping a subset relative to its measure over all subsets with measure less than 1 by 2. The classic result of Lovash and Shimonovitz states that the mixing rate of a Markov chain is inversely proportional to conductance squared from a warm start. To bound the conductance of this walk, we define 3 properties for a matrix function. These are convexity of the log determinant, symmetry, and strong self-concordance. A matrix function H is called nu-bar symmetry. A matrix function H is convex if the log determinant of Hx is a convex function. For the log barrier, the log determinant of Hessian is convex. The next property is nu-bar symmetry. A matrix function H is called nu-bar symmetric if for all points x in K, the Dickin ellipsoid of radius 1 is contained in the symmetric body K intersection 2x minus K, and the Dickin ellipsoid of radius square root nu-bar contains K intersection 2x minus K, which is illustrated here. For the Hessian of the log barrier, nu-bar is equal to m. Before defining strong self-concordance, we define self-concordance. For any convex set K, we say a matrix function H is self-concordant if for any x in K and a direction H in Rn, the absolute value of hx to the power minus half times directional derivative of h at x in the direction h times hx to the power minus half is spectrally bounded by the local norm of h at x. Intuitively, self-concordance measures the relative rate of change of the h function in spectral norm. If 2 points are close in the local norm, then their Hessians are spectrally close. Self-concordant barrier functions enable the random walk to take large steps in the interior of the polytope while avoiding the boundary. For example, the log barrier is a self-concordant function. However, self-concordance is not enough to remove the dependence on m. We need to strengthen the notion of closeness of the h function. This is where strong self-concordance comes in. It uses Frobenius norm rather than spectral norm. For a convex set K, we call the matrix function H strongly self-concordant if for all points x in K and h in Rn, the Frobenius norm of hx to the power minus half times the directional derivative of h at x in the direction h times hx to the power minus half is bounded by the local norm of h at x. Note that strong self-concordance implies self-concordance. Strong self-concordance also implies a nice property for the h function, that is for any 2 points x and y in K, if the distance between x and y is less than 1 in local norm at x, we have that the Frobenius norm of hx inverse hy is bounded by the distance between x and y in x norm. In other words, if 2 points are close in the local norm, then their Hessians are close in the Frobenius norm. Log barrier is strongly self-concordant. Intuitively, strong self-concordance measures the relative rate of change of the h function in Frobenius norm. To bound the conductance, we need to prove two things. First is isoperimetry, that is, large subsets of the body should have large boundaries. For this, we use a theorem of Lovász, stating that for any convex set K and disjoint subsets S1, S2, and S3 forming a partition of K, the volume of S3 is greater than equal to the cross ratio distance between S1 and S2 times the volume of S1 times volume of S2 divided by volume of K. Then we relate the cross ratio distance with the local distance in the following lemma. For any 2 points x and y in K, the cross ratio distance between x and y is greater than the local norm of local distance between x and y in the x norm divided by the square root of mu bar. The second thing that we need to ensure is one-stop distribution overlap. That is, points with a low probability of crossing over should be far apart. In other words, if 2 points are near, that is close in the local norm, then the distributions obtained after taking one step from them must have a large low overlap. We state this as the following lemma. For any 2 points x and y in P, such that the local distance between x and y is less than r divided by square root n, we have that the total variation distance between px and py is less than equal to 3 by 4, where px and py are the one-step distributions from x and y respectively. The combination of these lemmas proves that the conductance of the generalized Dickin walk Markov chain is omega of 1 by square root n nu bar, and therefore the mixing time is O star n nu bar. Now we present a proof outline of the second lemma, which uses all the three aforementioned properties. The total variation distance between one-step distributions of x and y is bounded by half rejection probability at x plus half rejection probability at y plus the total variation distance between the Dickin ellipsoids at x and the ellipsoid at y. Intuitively, we want that if the points x and y are close to each other, then the distributions on the ellipsoids around x and y must have a large overlap and hence a small total variation distance. Since the walk uses metropolis filter for rejection, we get the reject x term to account for the fact that the one-step distributions are not uniform. More formally, reject x is the rejection probability at x, that is, it is equal to 1 minus the minimum of 1 and the ratios of volume of ex and the volume of ez, where z is sampled uniformly from Dickin ellipsoid at x. And exa, we will use this to refer to the ellipsoid centered at x with matrix A and also to the uniform distribution on this ellipsoid. The total variation distance between the uniform distributions on ellipsoids ex and ey is equal to half volume of ex minus ey divided by volume of ex plus half volume of ey minus ex divided by volume ey. We can bound the right-hand side terms separately. First, we bound reject x. Let fz equal to log determinant of hz. Then f is a convex function, and therefore log of determinant of hz divided by determinant of hx is equal to fz minus fx, which is equal to the log of the rejection probability. And this quantity is greater than equal to gradient at x transpose z minus x. For a point z sampled uniformly at random from a ball of radius r around x, and for any vector v, using this concentration bound with probability at least 0.99, gradient at x transpose z minus x is greater than equal to minus 4r divided by square root n times 2 norm of gradient transpose hx to the power minus 1 by 2, which is greater than minus 4r. We get the last inequality by using strong self-concordance of h. Therefore, the rejection probability at x is less than equal to 1 minus e to the power minus 4r, and similarly, rejection probability at y is also less than equal to 1 minus e to the power 4r. Now, we can break down the ellipsoidal total variation distance into two terms using the triangular inequality. The total variation distance between the original Dickin ellipsoid centered at x and y can be broken. The total variation distance between the original Dickin ellipsoids at x and y can be broken down into the sum of total variation distances between the ellipsoid centered at x and y having the variance matrix hx, and the total variation distance between two ellipsoids, both centered at y having variance matrices hx and hy respectively. We can bound these two terms separately. Term 1 is the ratio of volumes and therefore invariant under the affine transformation x goes to hx to the power half z, after which it becomes the total variation distance between two balls of radius r whose centers are at a distance at most r divided by square root n. This was proved to be less than e divided by e plus 1 in Cannon et al. 1997. Term 2 is also ratio of volumes, and therefore we can assume that hy is equal to the identity matrix after an affine transformation. Let inverse eigenvalues of hx be lambda I. Then by strong self-concordance, the Frobenius norm of hx inverse minus I is less than equal to the distance between x and y in x norm, which is less than equal to 2r divided by square root n. This implies that the sum of squares of lambda I minus 1 is less than equal to 2r by square root n. We use this to show that the intersection of two ellipsoids is large. Consider an ellipsoid centered at y with inverse eigenvalues minimum of 1, lambda I along eigenvectors of x. Then I is contained in the intersection of the ellipsoid at y having variance matrix Hx and the ellipsoid at y having variance matrix Hy. And we can bound the volume of I using lambdas, which in turn bounds the total variation distance between the two ellipsoids. Now, in this section, we present an instantiation of the this completes a proof of the function defined by Lee and Sitford, which is as follows. For a point x in the interior of the polytope, let fxw be the function log determinant of ax transpose w to the power 1 minus 2 by q ax minus 1 by 2 minus 1 by q sum of wi's, where a capital W is the diagonal matrix having whose ith entry is equal to wi, and ax is equal to sx inverse a, and q is equal to 2 times 1 plus log m. Then the least Sitford barrier is equal to the maximum over all weights greater than equal to 0 of half of fxw. To define the Lx matrix function, for any point x in the polytope, let wx be the weights that maximize Ls barrier at x. Then the Ls matrix is defined as hx equal to 1 plus q squared times 1 plus q times ax transpose wx to the power 1 minus 2 by q ax. The Ls matrix satisfies all three of the aforementioned properties. The Ls barrier is convex, and for all x in the polytope, the maximum is achieved at a value of w such that the sum of the weights is equal to n. The Ls barrier can be restated as constant times log determinant of Ls matrix plus a constant, and hence the Ls matrix satisfies convexity. Ls barrier is also mu bar symmetric with symmetry parameter equal to 4e times log m cubed times n. This is only polylogarithmic in m, and again, it's because the sum of weights is equal to n. The Ls matrix is also strongly self-concordant. Since the Ls matrix satisfies the three properties needed for fast convergence, Dickin walk using Ls matrix, which can be seen as a weighted version of the standard Dickin walk, mixes in order n mu bar, which is O star n square. Every step of the barrier, the work of Hildebrand already establishes the convexity of log determinant function and strong self-concordance. The universal and entropic barriers, while these barriers are not efficient to evaluate, they are interesting because they achieve the best possible self-concordance parameter values for arbitrary convex sets and convex cones. For the entropic and universal barriers, we present an unexpected connection to the KLS conjecture. The strong self-concordance of the universal and entropic barrier is bounded by order psi n, where psi n is the KLS constant for isotropic log concave densities in Rn. The KLS conjecture states that for any isotropic log concave density, the conductance, that is 1 by psi n, is greater than a universal constant. Hence, the strong self-concordance of the universal and entropic barrier is implied by the KLS isoperimetry conjecture. This suggests possibility of more fruitful connections yet to be discovered using the notion of strong self-concordance. A few open problems to consider. Do there exist barrier functions which makes an order n square steps, and each step can be implemented in time order n square plus number of non-zeros in A? Can the Dickin walk with Ls matrix be used to make algorithms for volume computation faster? For example, using it as a component in the Gaussian cooling algorithm. Is the mixing rate of Dickin walk with Ls matrix order n? This concludes the talk. Please feel free to contact me with any questions.